Hi there guys, welcome back to Jordy's YouTube playlist of tips for beginners learning RStudio, and also for those that just want a refresher or recap of some of the most useful things you can do in RStudio. Don't forget that RStudio can be used for so many purposes. Most people use it for the kind of stuff we've done so far, graphs, statistics. But you can also write reports, which we'll get to at a later stage, and do bibliometric analysis, which maybe, if there's interest for it, comment below please. We can start doing some bibliometric analysis. You can also make apps, although I think that app making might be outside the scope of this playlist. Let's just see where it goes to. Really hoping for some interaction from you guys about what you'd like to see in future videos. For now, the obvious next step is to start modeling, okay? And what do I mean by that? Well, this was the script from our previous session, okay, our previous video. And you can clearly remember and get the idea that we were interested in relationships between a predictor and a response. And sometimes alternative words for predictor and response are, the predictor is called the independent variable and the response is called the dependent variable. I prefer predictor and response because I think that the words, independent variable only particularly makes sense in a modeling way, but it is just a column. Both of them are just columns of collected data. And it makes sense why the response would be called dependent, because it depends on the predictor. Maybe it doesn't though, okay? And you use statistics to find out if it does or doesn't. A model is really to see if there's a relationship where a change in the predictor causes a change in the response. And you can apply all kinds of models. The most simple models are probably things like t-tests, analysis of variance, linear models. Linear modeling allows you to find out if there's a straight line, okay? So the typical LM is looking at if there's a straight line relationship between, let me just draw something. Okay, between your predictor and your response. Sometimes when I'm teaching, I just draw things on paper, and let's do that now. Okay, so of course it makes sense to start with a graph, because by viewing the graph you should see already if there appears to be any kind of relationship, a straight line or otherwise, between your x and your y, your predictor and your response. What you can do, and we'll start by doing this, is fit a geom smoothing line. This is supposed to be a straight line. It's not particularly smooth. I'll make it look a little bit straighter. Okay, there's a straight line. Between points on the values on the x-axis and values on the y-axis. When you make a model, a linear model, you can get the other numbers, the other values which are required to create in a regression equation like this, okay? And these other numbers are m and c. Okay, so these are what we call the regression coefficients. And the output in RStudio, when you check the summary for a linear model, you will tell you those numbers. Okay, so that means that if you, for any given value of x, whatever your x is, you could plug that number in together with the results for the m and the c, and you could get a prediction of y. Another reason why it makes sense to do the modeling stuff now is because we've already looked at code such as favstats, which is inside Mosaic library. The favstats syntax, okay, here is very, very similar to the model syntax for an LM. So it makes sense, since we know that, to continue with model syntax and modeling. Let's look at one of my favorite data frames today. I know it's not diamonds. I feel like maybe we'll take a break from diamonds for a few weeks. Let's look at Faraway library. So this is a library in RStudio that I found a few years ago, and the thing that I like about it is it's got hundreds and hundreds of data frames. In fact, it's got data frames across so many different subjects. There's one called broccoli, and there's ones about health and animals, and there's stuff about cancer, and so many different subjects and data are included within this library. You just need to load the library, know the name of the data frame that you're searching for. You can ask me if you want a list. I probably won't make that public, I'm not sure. It's not my library. And definitely the creator, developer of that library should get all the credit. I believe the person's name is Faraway. What I can do is I can show you my favorite data frame within it, which is the Gala data frame. So the Gala data frame is my favorite data frame in Faraway because it's in line with my background in oceanography and ecology. These are the data on tortoises in the Galapagos Islands. So this data frame's a little bit like the empty cars data frame in that the rows are named instead of numbered. Okay, so you remember from empty cars we see the same thing with, instead of having 1, 2, 3, 4, 5 as the row numbers, we've got names of cars. Okay, and that only works if the row names are unique. So in this case, no car is listed twice. You can do that if you have a column that you want to turn into the row names where all the values are unique. With the Gala data frame, these islands all have separate names. And let's have a look at some of the data then. Okay, firstly, all the columns contain numeric data. That's possible because the only column with words in it has been put as a row name, so it doesn't really count as a column anymore. All of these are numerical, so I'm expecting if we do an str of Gala, we'll see that information there. Yes, every column here, these are the columns and these are dollar signs next to the column titles. After that we see num for every column, meaning that that is a numeric column. Num or int will be numeric columns. Int is integer, num is where there are decimals in that column. Okay, so no longer all integers. And chr is character, so that would be different. The idea in this data frame is that you've got counts of species on each island, as well as information about the island. Interesting columns are the number of species and the number of endemic species. So you see that the number of endemic species is always less than the total number of species. Some of these are endemics, which mean they're only found in that place and nowhere else. And this is something that happens in the Galapagos Islands, right? There's a lot of species only found in a specific Galapagos Island and nowhere else. And I love that. I think that's really cool. We actually learned about the Galapagos Islands in high school with Darwin's finches. Okay, it was like how the beaks of the birds had evolved in different ways, you know, to eat different items like seeds and animals and bugs. And so the idea probably would be, or the question would look at how changing the distance to the nearest island affects the number of endemics. The idea would be that when an island is more remote and further away from any other island, that there would be more endemics there because they would be less able to travel to another island. There might also be an impact of area and elevation, height, on how many species are found on a given island. So this is kind of cool stuff about animals and where they're found. And this is for tortoises. So there's different ways to approach modeling. If we go back to the script now, you might actually just want to see if any of these other columns affect the number of species. And to do that, we can make a LM model where we're going to call it something first, just like we named the plot. For the purpose of patchwork, we can name a model. And when we name it, that means that we can then get summary statistics from that model just by calling on its name. Let's see then, let's make an LM model called Gala model. LM, that means linear model, again, this thing. And if we keep it like this, okay, LM, and we don't turn it into something called a GLM, it's going to give us something like this. It's going to be interested in this relationship, whereby X could be any other column apart from species, and Y will be the species column. Okay, data equals Gala. That's similar to in a ggplot where you put the data equals and name of the data frame. Let's look at species. Again, we need to spell things exactly as they're spelt here. But what we can do for now is just do squiggly line dot. And that squiggly line dot, okay, it's called a tilde, but I'm always just calling it a squiggly line, signifies interested in any other column apart from species as possible predictors. Okay. Now this might not actually be the way that we continue, because you might find out that or you might think about it logically and figure out that there's no reason to include endemics as a predictor. Typically endemics would be a response, right? So why would you have endemics as a predictor for the number of species unless there is something going on there? That's where you need to look back more into the textbooks and understand your specific subject to help you come up with a good model question in the first place. That's sometimes what I spend quite a lot of time on, just helping students come up with the best questions for their project, and either what data they need to collect in the first place or what should be included in the final model. Okay, so we're going to run this. It worked. Now we're going to do a summary of the name of the model, Gala model. Okay, so we get some interesting things here. Okay, this is very interesting. What I'm going to do first is I'm going to add another line in here. Options SCIPN equals 999. Strange word, but it's basically going to help us to understand the model outputs a little bit more from the summary. That's because it's turned all of these numbers under this column, PR, higher than T, as into decimals, okay? Now let's talk a little bit about what this column is. These are p-values. And this is probably the main way that people see if there's an effect of a predictor on a response. So we'll maybe have to spend a bit more time on p-values and model outputs in future sessions, but basically this is the way that you look at significance. Okay, and I don't mean significance in kind of the layman public way, I mean in terms of statistical significance. When this number for any given column is less than typically 0.05, that's considered to be less than 5% chance of the observation occurring by randomness, by random chance. And all of this can be related to in terms of what's called the null hypothesis. The null hypothesis is where there is no effect of any one of these columns on the species column. Okay, and it means that there's less than 5% probability that that observation would occur if the null hypothesis, if the no effect was real. Okay. Now, this is I'm always just like trying things for the first time, and maybe I've never made a model of this one before. It's interesting to see then that in this linear model, anything that might have affected species, such as area, the elevation nearest, etc., is turning out to be higher than 0.05. What you can do is you can narrow it down, and you can, instead of making a Gala model on all the columns, we just make a Gala model on one predictor, okay? Species, squiggly line, area. So this then becomes a univariate model, just as a single predictor, uni-predictor model, looking at possible, let's say possible, effect of changing area on the number of species. Okay. So then we can do a summary of the Gala model 2. Simple lines there. Okay, right, so this is important. Now we actually do have a significant p-value. We have a p-value less than 0.05. What's obviously happened is there was too much going on in the original model, and also stuff that probably shouldn't have been in it, such as the number of endemics. And this was actually due to some stuff going on in the background that we don't really need to go so technical on, is actually changing the p-values of all the numbers, of all the columns. So I recommend keep your model simple. Okay, start with a simple question. How does area affect species? We can add to it. You can make a bivariate model by adding a plus and then elevation to add elevation into it. But we get this line here, okay? And this is the line that I think we need to focus on first. Sorry about that. We can copy it, okay? And I'll put a P in front of this. So we want to copy it into the notes. When I did a course before, we were asked to keep very strong, good notes in the script for the lecturer. So I think that that's important, also for yourself, just to keep a note about what you're doing in your coding. The script can very much be like a diary for leaving notes to yourself about what you've done and your learning. Okay, we've got these numbers now. Let's focus a little bit more on the p-value, and we're just going to call this p-value. This is a p-value, like I said, p-value is probability of an effect of area on species, okay? But that's better written actually as probability of same observation occurring due to random chance. I mean, there's different ways to say it, okay? If there is no effect. So the reason why we compare this with what we call this number, what we call an alpha of 0.05. That's the 5% thing that I was talking about. And 5% is pretty reasonable, okay? It's pretty good for the randomness. The randomness factor. Okay. So we want, or we don't want, but we would call p-value less than this, sorry, less than 0.05 significant. Typically. Now, people sometimes use 0.01. Okay, that's 5%. 0.01 would be 1%. That would obviously mean you're even more confident. So that's the first thing. If we get into this column here, the estimates column, these are the two numbers that go back to this equation, y equals mx plus c. So the number here, okay, the number here is the m, okay, we call these, let's call them regression coefficients. Okay, that's the m, leave a hashtag here, m equals, I know in different countries they use different letters for that equation, like y equals ax plus b, but in the UK we learned in school, at least when I was young, y equals mx plus c, regression equation. Straight line. Okay, so this is the m, the number here next to area, or the number next to the name of your predictor. Name of your predictor. And this is c, okay, which is the number next to the intercept. C equals number next to intercept. That's the intercept word. That then means that your model equation is y equals, sorry, I'm sure you already know, okay, I'm sure you've already kind of figured it out already, but y equals this number x, let's just leave spaces to make it nice and clean, plus this number. Okay, it probably makes sense to put this bit in brackets so that when you're doing your calculation we don't accidentally add this number to the x number, and x could be any number that you have that you want predicted, you know, you want a prediction for. So let's take a look now at a ggplot graph, just a scatter plot of the contents of the model. Also, I feel like we've talked a bit about regression and about regression equations, but I want to emphasize the point that modeling allows you to predict something. That's the reason we have that equation. So we are trying to predict y from these other numbers. It's not going to be perfect, okay? Of course, you're not likely to find a perfect model. And the next session, I will talk about how we can see how good our model actually is. But it will give you a reasonable, hopefully if you make a reasonable model, you can get a reasonable estimate of what y could be around with a given value of x, okay? Let's do a ggplot, okay? Data equals Gala, okay? AES, which is aesthetics of the graph, and here we put the x and the y. Okay, x, that's obviously predictor variable, and here we have area. Y is going to be the species number, the number of species. I mean, that's a reasonable question, okay? How does area affect the number of species? As you have a larger area, you would expect to find more species there because there's more spaces for them to hide, to hunt. There would be microhabitats. There would be like niches available. They can go higher up the mountain, if there is a mountain. Geom point to turn this into a scatter plot. Okay, we'll run that for now. Yeah. Interesting graph. So this is cool because the vast majority of the data is skewed towards one side of the graph. There's one island, right, single island here. I think it's Isabella, maybe, which has a very large area, much larger area than the other ones. Okay, but I'm not trying to remove it for now. Maybe we'll keep it in. If we want to remove things like this to see how the model changes, we can do that in future sessions. For now, we can just work with the entire dataset. But the point is to add a smoothing line, and this is going to fit the model onto the graph. Okay, so if we do method equals lm, that's going to put the model line onto the graph. Okay, so this is the regression smoothing line. This is our equation. Y, or this has the equation, this blue line here. Y equals 0.08 x multiplied by x plus 63.8. Let's take a given value of x. So let's take for example, this, right, 2000. Imagine we have an island of 2000. I would prefer it if data frames had units in them. You know, that's kind of a pet peeve when they don't have units in them and we have to go online and figure out what the units of the island area are. It would be cool if it was already in the data frame. But anyway, let's imagine this is 2000 and that will be our x. Okay, so what we can do is we can predict y for x equals 2000 using the model. And if you're just trying to do this for a single value, it would be easy just to type the equation in and we can use our type of calculation. And we can use RStudio as a calculator, just like we can Excel. What I'll just do is I'll just copy this. Okay, but not the y equals. And I'll put an asterisk here, so we're multiplying, okay, which is this symbol here, multiplying by 2000. So here's your m, here's your x, here's your c. Let's run this now and see what number we get. Alright, we get a number, a predicted y. So this is our prediction of number of species for an island, 227.7. For an island of 2000 area, 227.7. Let's see how close that is to the blue line, to 2000 up to here. Yep, this looks about right. Here we are, 227. So you can clearly see then that we have been able to predict number of species for an island's area of 2000. I'm expecting in the next session to look at whether this is a good model or not. And you might already have your ideas about that. I mean, I've already suggested that a lot of the points are skewed on one side and they're not really spread evenly over the x-axis. So we might have a challenge with that. I would also expect that this point here is really the only reason, you know, why could be the only reason why we're seeing this trend. And if it wasn't for this, the line, it would potentially be linear, but maybe not. Okay, so when you have a case that your linear model might not be right, there are other alternatives, right? So you can do some transformation of your data, or you could consider other models, or you could maybe come up with another question or use other predictors. Anyway, I'll leave it there for now. I'll put this script on the drive, the Figshare, like I did for the previous sessions. This has really now opened the door to making cool models for cool projects, cool questions. I hope you enjoyed this. Stay tuned for more modeling with me. Have a good day.